I will demonstrate how to design a standard involute gear with geometry of the teeth synthesized based on mechanism motion. I will first create a rack that follows proper standards, then a blank gear, create a mechanism that engages the two components according to the proper transmission ratio. I will then synthesize the geometry based on motion, making one tooth of the rack cut its way into the blank gear. The other teeth will be simply made with a pattern. To demonstrate that the gear made follows the proper standards, I will also engage it with a standard gear taken from the internet. Select working directory, create a new part called rack, tools, relations, and here let's take some of the relations that I have already done, copy from here, paste them in. I'm gonna say OK and model regenerate to load those parameters. Create a plane with an offset from the right plane, pull it arbitrarily to the right. This will be used to reference the first tooth. I'm going to call it TRA for a translational plane. Create an extrude in the front plane for which the references are right will be deleted and replaced with the TRA plane. Close, place that in sketch view, and let's hide everything. Create a first vertical center line, and then here a line that snaps zoom in and a line that snaps symmetric. The size of this should be on the order of 1 millimeter. I'm going to take it closer to the axis and zoom in. Create 2 points, one here and one here. They should be symmetric with respect to the vertical. The distance between the 2 points from here to here is pi over 2. Enter, and I will not enter that as a relation for the moment. Create a line that goes here, passes through the point and goes here, and maybe to the left as well, and comes down and comes on the other side. And create another line that goes from the other end, comes through the line and to this level. It closes the profile. These 2 points are symmetric with respect to the vertical, this point and this point, and so are the other ones at the ends, right here. And moreover, the point here is the midline of this line. And then we have dimensions from here to here. That is going to be 1.25. We will overwrite that from the relations. The angle between the flank and the center is going to be 20 degrees. That will become the pressure angle. The width of one tooth will be pi. Again, no relation at this moment. Let's say the height of the entire construction from the bottom to the pitch line, 6 millimeters. This is one tooth. Let's take a default view. Extrude this mid plane with a distance of 5 millimeters. Okay. Color it. And save the work. Now, let's also add rounds on the top and the bottom edges of the tooth. Size is 0.25. I'm going to say OK here. Let's group the TRA plane with everything into a group that will be one tooth. Then we will pattern this along the location of the plane with a pitch of pi. No. And create a number of 31 of these instances. Okay. relocate the original plane, TRA, at 0. Model, regenerate. Tools, relations. Maybe take a view from the front. Make this first tooth larger. And switch dimensions so that we can properly add the numbers. This number right here is going to be pitch over 2. This number right here is going to be module plus AD coefficient. This number here will be the pressure angle. The width of one tooth, which is this, should equal the entire pitch. The radius at the top of the tooth, it's here. This should be equal to the AD coefficient. Repaint. Let's take a look at the parameters of the pattern. This is the pitch, so should equal pitch P, and the number of instances should be Z plus 1. Okay. Model, regenerate. Finally, let's take a default view. We'll create an axis at the intersection of the top and front planes. Axis can be pulled up, which will be used for the slider joint in the assembly. Save the work and close. Create a new part, that is the gear. Let's go at the relations. And again, I will copy these relations here and edit them locally. Control V paste. I do not need this. It does not need the other coefficients. So I'm going to take them out. Okay. Model, regenerate. Here we will create a revolve in the right plane, putting this one top to the top. Sketch and take a look into the sketch view. We do not want to see the planes in this case. I'm going to hide them. Revolution axis is horizontal. Another one, center line vertical for symmetry. Take a line that goes from here to here. The width of this line is 5 millimeters. The height, we will overwrite that parametrically. I'm just going to put it 20 millimeters for the moment. Then we're going to take a line and come in here, and then here, and then here, and here. Close. The hub of the gear will be 7 millimeters. Let's say that it's also 10 millimeters in diameter with a 5 millimeters bore. Okay, take a look. Okay, and default. Set a color for this one. Let's say this red. Save. Looking at the relations, we will make it so that, let's say, view from the right. The outer diameter of the gear, which is this, equals our OD. Okay. Model, regenerate, and save. The axis at the center will be used for the pin joint in the assembly. Save and close. Create a new assembly, that is the rack, and is in assembly. Create the horizontal axis and hide the planes. Assemble the rack with a slider that goes axis, front plane with front plane. And taking a look from the front, we would also like to set the 0 position between the right component, right planes of both components. Place that in 0. Let's give it a positive number to observe the direction, and that is good. I'm going to keep it as is. Why don't we enable regeneration value as well? We're going to say OK. Save the work. create a plane with an offset of 15 millimeters from the top, and another axis at the intersection of this with the right plane. Axis is here. Hide the rack at this moment so that we can assemble the gear with respect to the assembly with a pin that goes axis on axis, front plane with the front plane of the gear. And taking a look at this from the front, we're also going to set the 0 rotation between the right and right planes. Let's see the direction of rotation. 30 degrees are moving to the right, and that is good. We're going to keep it as is and enable the regeneration value. Show the rack and take a default view. Let's now centralize the parameters into the assembly. So let's take them from the part, which is the rack first. So I'm going to come into the rack and delete everything from here. X. Okay. Move this one to the assembly, the rack, and paste them in. At this moment, I would have to move all the parameters. Let's find out the session ID of the rack part, and that is session ID 0. I'm going to say module of component 0 follows the module here. The pressure angle of component 0 follows pressure angle here. AD of component 0 follows AD here. And Z of component 0 follows Z local. The same way we're going to do it for the gear. So let's get session ID of the gear part, and that is session ID number 2. We will only need it for M and Z. So in that case, we're going to say module of 2 equals local module, and we're also taking the relations of that part so that we disable it up front. Okay, and model regenerate. Right now all parameters are driven from the assembly. With that, we can also set the location of the plane, which is positioning the gear. This location right in here should be M times Z divided by 2. Model, regenerate, and save. Applications mechanism, create a connection gear, new, that is a rack and pinion, for which the pinion is the pin joint of the gear, and it has a pitch diameter of 30, and the rack is the slider joint. I'm gonna say okay. Let's say close it here. Go and create a snapshot at the current location. We're gonna call this 1, 0. Close. Show the right plane of the gear and drag the components. You can see how the gear is properly engaged with the rack, even in the absence of the teeth. Take a view from the front. Take a snapshot based on a constraint, let's say angle of motion of the pin joint going to minus 35 degrees, and take a snapshot here, minus 35, and we will engage it in motion all the way to 35 degrees when the tooth comes out of engagement. Okay, and close. Create a mechanism motor, servo new, which acts on the pin joint and is driven on angular velocity with 70 degrees per second, that is 2 times 35. I'm gonna say OK and create a new analysis that is called synthesis, working for 1 second with many frames, 200 frames per second, starting from snapshot minus 35, run. Comes in and out of the engagement. In preparation for the synthesis curves, we're going to open the rack part and create a sketch in the front plane, placing that in sketch and coming right in. Maybe remove all the references, delete, and add this and this and this and this one right here. So with that, we're going to get the profile of the tooth, skipping the radii. Okay, take a default view. This is the profile that we have made. Save the work and close this. Coming back to the mechanism, maybe run the analysis again. It comes in and it comes right out. So with this, we're going to do an analysis trace curve with the paper part on the gear. That will be a cam synthesis curve, for which the curve is this piece. And say OK and plot it for synthesis. And OK. Do the same for the other 2 parts of the tooth profile. Paper part here, synthesis curve being this. OK. And preview and OK. Once more, paper part is this, synthesis curve. The curve is the other side of the tooth. OK. Preview and OK. Save the work. Open the gear. Yes, save the playback results. Take a look at this from the front, in motion. Observe that this curve is needed, this curve is not needed, so I'm going to delete it. The next curve is not needed, so I will delete it. This curve here is needed, whereas this curve here is not needed. So with that, we have been able to simplify the profile, in which you can already see the geometry of the tooth. Do an extrude in the front plane. Here we will project this curve and this curve and this curve here. And then we will use a corner in order to corner this curve once it intersects this curve here. And I'm doing that with left and control left click. And with that, you see how the curve has just remained describing the profile. We will remove material all the way through on both sides. And that is one tooth. Create a round that goes here and goes here. The size is 0.25. It will be equal to AD coefficient. Group the 2 components. And let's show the axis. Pattern the group with an axis option about the central axis, creating 30 of these teeth equally distributed. We do not want to see the curves, so we're going to take a default view. The right plane also hidden. Save the work and close this. Coming right as taking a view from the front. You see how the teeth are perfectly interdigitated. And if I'm going to take this and move it, you see that in motion the engagement is perfect. There is no clearance, there is no interference. Close. Finally, to demonstrate that This gear is a proper standard gear. We will engage it with another one, which I have taken from the internet. That is, open this part right here. It was specifically taken from SDPSI. So with this, I'm going to close it. I will create first, come out of the mechanism for the moment, create a plane that has an offset with respect to the previous one. The offset here will be pitch diameter of one, which is 30, plus pitch diameter of the other divided by 2. The gear I have taken has a 15 millimeters pitch diameter. Create an axis between this and the right plane. We do not want to see this plane. And finally, let's hide the gear so that we can assemble with a pin connection that goes axis with axis here, and front plane with front plane of the gear, and say OK. Show the other gear that we have made. Take a look at this from the front, and of course they're not properly interdigitated yet. So to do that, I'm going to come to and set a 0, edit the definition of the new gear, placement, set the rotation 0 between the right plane of the assembly and the right plane of the part. And then with this, if we're going to turn it 360 divided by the number of teeth divided by 2, that will be exactly half a tooth. Let's set this 12 degrees to become the 0 position and enable the regeneration value as well. And then enter a positive value, let's say 30 degrees right here, which moves me in the incorrect direction. So I'm going to flip this connection and put it right back to the 0. Okay. Save. Update the snapshot, 0 degrees, update it with the new part. Applications mechanism, let's define a new connection gear that acts between the pin of the big gear, which has a 30 millimeters pitch diameter, and the pin of the little gear, which has a 15 millimeters pitch diameter. Okay. And with this, if we're going to go to mechanism and zoom into the position of the teeth, you will see how well the new gear also engages the gear that we have made. Now, the way that the two gears have been made are substantially different. We have made this synthesizing geometry based on motion, whereas the other gear has been defined by involute curves. Save the work, take a default view, and save.